And now we get into the stretches. In other words, dilations. We're stretching the graph, we're grabbing a hold of it and pulling or pushing one way or another. If we have this p times f of x, outside the function it is vertical, and we say it has a scale factor of p. If p is greater than 1, we will move further from the x-axis. Makes sense. If it's 2 times f of x, that means it's going to get 2 times as tall. If p is a fraction, p is between 0 and 1, it moves the points closer to the x-axis. So we're smushing it. We are stepping on the top of it. We're making it shorter. Everything gets lower, closer to the x-axis. If we have f of q times x, so the scale factor is now inside the function with the x, that means we are going to have a horizontal stretch or compression or a horizontal dilation, and the scale factor will be 1 over q. If q is greater than 1, we will move closer to the y-axis. Closer to the y-axis, but, well, it's kind of the same thing as the horizontal translation. Inside the function with the x, it's opposite of what you would think. If q is greater than 1, we go closer to the y-axis. If q is less than 1, a fraction, we move further from the y-axis. And that's where this scale factor 1 over q is. The old mathematicians decided, you know, we're going to make things difficult for you. Anytime this translation or scale factor is outside the function, it's going to be just like what it says. But if it's inside the function with the x, it's going to be opposite. We'll see how many people we can get to forget that part of this. Not really, but it's what I like to say. So, here we are. For f of x equals x squared, graph g of x and h of x. So again, I'm going to start with the basic graph. Of y equals x squared. So there's f of x. Now I want g of x to be 2 times f of x. That means the scale factor of 2. And it's a vertical scale factor. So everything just gets taller by 2. So this point right here, that was 1, 1, we make it twice as tall. One comma 2. This point that was 2 comma 4 becomes 2 comma 8. And similarly on the other side. Now what's 2 times 0? It's 0. So that point does not move. And you can see that this graph has become quite a bit more steep. We've sort of grabbed onto the ends of this parabola and pulled them straight upwards. This point right here that didn't move, that's called an invariant point. It doesn't vary under this transformation. So it has a special name, an invariant point. Just some terminology that you will see throughout this chapter. Now we want h of x to be f of 2x. So this is a horizontal scale factor of not 2, but 1/2. What that means is that all of these points are going to stay at the same height, but they're going to get closer to the y-axis half as much. So this point that was at 1 comma 1 becomes 1/2 1. This point that was at 2 comma 4 becomes 1 comma 4. And you can see that this is a horizontal compression. We've gotten closer to the y-axis. The blue graph is a vertical expansion. We've gotten further away from the x-axis with our points. And although these can both be considered one or the other, the horizontal compression is really the same thing as a vertical expansion. However, it depends on how the function is written on what we're going to identify it as. So this is a vertical expansion with a scale factor of 2. This would be a horizontal compression with a scale factor of 1/2.